Hi everyone. In this lecture, we are discussing fuzzy intersection, which we also call T-norm. This one is an introductory lecture. So in this lecture, we'll be discussing only standard T-norm and axiomatic skeleton of T-norm. In the next lectures, we'll be discussing different types of T-norms. Thus, fuzzy intersection, and this fuzzy intersection is also called T-norm. So in fuzzy, we usually call it T-norm in spite of saying this as a fuzzy intersection, right? So let us start to understand what exactly is intersection. So we'll define this as a function, say I. Since it is intersection, we are defining it with, say, I. So it will be a map from 0, 1 cross, say, 0, 1 to 0, 1. And why is this so? Because here we are taking a membership grade, mu A. Here we are taking another membership grade, say mu bx, and the output, that is the image of the function, will again be a membership grade because it is a fuzzy set. So the fuzzy set I, or the fuzzy intersection of two fuzzy sets, say this I, is defined on, say, A and B, and it is defined in this way, right? So we denote it as, say, mu A intersection Bx is equal to intersection of, so this is the intersection function, membership grade first, and then we'll write the second membership grade. Okay, and this holds for every x. Here, this function I is called the T-norm. So what is T-norm of fuzzy intersection? So this T-norm is nothing but it's a function from 0, 1 cross 0, 1 to 0, 1. So if you take a lattice, then it will be from L cross L to L, but here we are restricting ourselves to 0, 1 interval only. Okay. So let us move further. So let us define first fuzzy intersection, that is standard intersection. And this standard intersection is basically derived from our classical concept, students. So if you see, this is basically from classical concept. So how do we define this standard one? We define the standard one as mu A intersection B x. How do we define the image? See, we had defined it in this way, right? So how are you going to define an image? Mu A intersection B as minima of the membership grades, mu B x. Now how do you define these minima? See, at some point, say A, if this mu ax takes minimum value, then A intersection B is going to take mu ax value. Suppose at another point, say D, mu bx is taking the minimum value, then A intersection B is defined by that way. If we define a, say, trapezoidal function, one by, you can say, mu ax, and another trapezoidal function also, say mu bx, right? So this one is mu x, and let the height be 1. Okay, so what will be this mu A intersection B, students? This mu A intersection B will be the minima. So if we move like this from here, let us see if this is say mu ax and this one is say mu bx. So here the first membership function, both the membership functions take 0 value. So this is going to take the minima, that is 0. And further, mu bx takes 0 values. So this is going to take 0 value here. And the minima then again is taken by mu bx, and then it will go like this. If we say this again, here in this interval, the minimum value will be this. Further, if we see, the minimum value is taken by mu ax. So this will be the graph represented by the green line. This is basically our mu a intersection b x. So unlike our classical concept, in fuzzy set theory, we have a function, we have few properties. If the function satisfy these properties, then this function is said to be a fuzzy intersection. So basically, what are the axioms which it should satisfy? We'll write that. So I'm giving it the heading as requirement of the T-norm. If you're studied in classical mathematics, there was one intersection. There was only one intersection, and here in fuzzy we'll define different types of intersection. The first one was the standard intersection, which is defined here. Let us move to those axioms. If satisfied, the function is called a fuzzy intersection. So axioms of the intersection function. Perfect. So from this, the first axiom is monotonic. So I'm not going to write again that yes, the intersection function again is obviously from as defined above 0, 1 cross 0, 1 to 0, 1. Now this function I has to be monotonic. So what does this monotonic means? That is, if suppose there is a membership grade, suppose this membership grade is written by B, which is basically our say mu bx. And in order to recall this, what is this our mu bx? It takes value 1 if x is in B and 0 otherwise. Okay, perfect. And let us take another membership grade, say mu dx, defined similarly. So monotonic means if the membership grade of B is less than D, then the intersection function of AB is always less than equal to intersection function of AD. So I hope this is clear. If B is less than equal to D, and then this follows. So this is the property of monotonicity only. Okay. So if we generalize this property of monotonic, so how do we write this? So in general, we take both the parameters, like we fixed here A. A here was fixed. This time we are not going to fix this A, and we say that if the membership grade of A is less than equal to C and the membership grade of B is less than equal to D, then the intersection function, that is in classical way, say that intersection of AB is less than equal to intersection of CD. Right? Second property, we are going to take is commutativity. Students, this is same as we studied in algebra, the commutative property. What does this says? If suppose membership values of, let us understand what was there in commutativity in classical. So if you remember classical, we used to say intersection is commutative if A intersection B is equal to B intersection A. If you remember this, we used to do this in classical one. Okay, now in fuzzy one, what does this means? That is, this function, which function? Mu A intersection B is always same as mu B intersection A. And we can say that mu A intersection B is equal to mu B intersection A, and this holds for every x, right? So in the way which we are studying, we can write this as intersection of AB is equal to intersection of BA. I hope this is clear. Let us move to associative property. Third is associative. So if you remember, in classical, how do we write the associative property? A intersection B intersection C is equal to A intersection B and intersection C. So we can group it in any way. So associativity in fuzzy, what does this means? This means that the membership grade of A intersection B intersection C is same as the membership grade of A intersection B intersection C. So this should hold for every x in capital X. Okay. So in the way we defined it in terms of the functions, we can write this as intersection of A and for the intersection of BC is same as if we take first the intersection of AB and then take intersection of C. So, and let us remove this, and yes, it is there, C. So this is the associative. Next comes the boundary condition. Boundary condition. Let us try to so let us try to understand this in classical way. See, try to correlate the things from with which we had already studied. So intersection, this boundary condition means if we take the intersection of A, the fuzzy set A, with the fuzzy set say 1. What does this fuzzy set means? This means that it takes value 1. So this will come out to be A. So if you remember, if you want to understand this or you want to translate, exact translation is not possible, students, but if we want to translate it from classical, we can always say that, think like this, that is a better word, think like this, that A intersection X, what this used to be A. So that is why A, because it is taking value A intersection 1 is A. Or since it is commutative also, so we can say that this is A. Students, these 4 properties are 4 axioms if any function satisfies these four axioms, then it is said to be a fuzzy intersection. And we call these four axioms also as the axiomatic skeleton of fuzzy intersection. Axiomatic skeleton of fuzzy intersection. Perfect. So this is all from my side. In the next lecture, we'll be discussing different types of T-norms.